So let's have a look at ordinary differential equations, how we find solutions to them. Now these ordinary differential equations can be zero-dimensional studies. When I say zero-dimensional, it is being differentiated only with respect to time, so it's a transient problem. We may also have one-dimensional steady-state problems, as we'll be seeing this example. It's a one-dimensional steady-state problem in which, again, the independent variable here is only one, which is, in this case, it's x. In some other cases, dynamic studies, we may also have only time as the only independent variable. And often it's all about tricks in integration with which you can exploit and get a solution for your problem, but there are also numerical methods available like Euler's method or Ronji-Cotta scheme. Let's have a look at this problem. A second derivative with respect to x of the x velocity u minus 2 is equal to 0, and the domain which has been defined for x is between 0 and 1, and the boundary conditions are given. X is the independent variable in this case, which is lying between 0 and 1, and we are having the boundary conditions there. It's a typical wave equation, and we have an exact solution for it. We have x velocity as a function of x, that is x squared minus x. So it's a typical pressure wave which we can try to imagine. Now exact solution was quite easy in this case. There can be more complicated situations, but let's try to see how we can apply a numerical scheme like finite difference method. Now I'm going to show you finite difference method to be applied on an ordinary differential equation, not the Ronji-Cotta scheme or Euler's method, but I'm going to show you the finite difference method in space. In finite difference method, what we have is the 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 forward difference and backward difference schemes being applied. So we may have, let's say this is the curve of the quantity u with respect to x direction, and let's imagine this is the curve. In that case, we know what a forward difference and backward difference means, and we also have something called central differencing. So this is how we try to find out the slope. Actually, the first derivative represents the slope at any point. So we have this x coordinate being divided in the form of some subscripts like I minus 1, I and I plus 1 points, and the distance between two adjacent points, adjacent grid points, as you can see here, is delta x. So in that case, the second derivative can be written in the form of the first derivative's first derivative, and that's why we get 1 upon delta x. That's a numerical approach, and using the first order term of the Taylor series expansion, we have an equation of this form. Now what this shows here is that we have truncated some terms. Now this is where the truncation error comes. We have not included the second order or the high order terms. We are just assuming d by dx as a difference equation, as you can see here. So that's where the truncation comes into picture. We'll be speaking more about it, what this truncation error is, in the subsequent slides. But I guess you can remember this, that CFD involves truncation errors, round off errors, and modeling errors. And this truncation error is something which comes up here. So let's say we have our space between x is equal to 0 and x is equal to 1 being divided into say 3 points. That's ui plus 1, ui minus 1. These are the extremities, and in between you have ui. In that case, you can use this finite difference formulation and you can express the second derivative in this form, and we get an expression for ui here. So this expression for ui, if we try to apply the boundary conditions of ui plus 1 and ui minus 1, and we apply the value of delta x, that is delta x because the region between 0 and 1 has been divided into two parts, that's why you have this delta x to be half, and in that case we have ui being equal to minus 1 upon 4 according to this equation that you see here. That's a finite difference formulation. And if you compare it with the analytical solution, the exact solution quite drastically matches here. And that's what I want you to appreciate, that this numerical solutions can give you the exact solution in several cases. But compare it to the exact solution. In exact solution, you can put in your specific value of x and you get the value of u, unlike the finite difference formulation where you get such numbers only at selected locations. In this case, we have the values at ui plus 1 and ui minus 1, which is the boundary condition, and we have only one value in between, that is at x is equal to half. Now that's the difference between an exact solution and a finite solution. Using numerical schemes, that you get values only at specific locations. Now partial differential equations also follow a similar philosophy for getting solved through the methods like finite difference, finite volume, or finite element method, although there are a variety of other methods by which people have tried to solve the equations which govern the fluid flow, because they are most of the time partial differential equations. Now for such partial differential equations, these methods like finite difference, finite volume, and finite element, they all require one common thing, which is grid generation. That is, the space x and y dimensions, or z dimensions if it's a three-dimensional problem, has to be discretized. Now there are some good reasons why people are interested in these other methods apart from the finite methods that you see here. That's because of this additional step of grid generation which is required in the case of these finite methods like finite difference, finite volume, or finite element. So people are trying to come up with gridless methods, and that's why it is provoking some kind of interest in the scientific community to try to explore some other methods, other numerical schemes apart from the conventional methods to solve these partial differential equations. The task we are having in the case of any problem solution of fluid flow is to solve these partial differential equations, which are actually highly nonlinear, and they are second order partial differential equations. They become second order because of the diffusion term, and they are nonlinear because they contain, if you can just try to recollect, the second term on the left hand side in the partial differential equation consists of the velocity field convecting the property phi, where the property phi can also be in some cases u, v, and w. That's why it becomes a nonlinear equation. So exact solutions are only possible for some simple flows, but for most of the flows we can't try to get to the exact solution. We have to use numerical solutions. And this is where we need to understand that we need a grid. Now grid is something which helps us to divide the geometry into smaller fragments, and it is through dividing the geometry into smaller fragments that we can apply the finite methods. So if someone asks you what is the reason that we um, require a grid, the reason is because the numerical scheme requires a grid. Not that on our own, if we were solving it exactly, we would need it, but the numerical scheme that we are using are finite methods like finite difference or finite volume or finite element methods, and they require the geometry to be discretized. They try to apply the conservation equations on these discretized geometry over each and every element or each and every volume, or in the case of finite difference method, each and every grid point. And it is at these locations that the equations are applied using the numerical scheme, and then the solution is found out at those specific locations. And these values, when they are all plotted together, we have the results of the simulation. We have the results of the CFD analysis. That's why we require a grid. We require the grid so that the numerical scheme can be applied, which will solve the continuous form of the partial differential equation through a discretization scheme. So this is what it looks like. We have a continuous geometry. We may be able to apply a calculus based solution for this, but which is not possible for partial differential equations. That's why we have a discretized geometry. We divide the geometry into smaller fragments. That's called mesh. We move on. We have the methods now. We have the finite difference method, which is one of these methods with which you can apply on a discretized geometry to find a solution for the governing equations of fluid flow and heat transfer. Finite difference method is the oldest of the three finite methods which were already mentioned: finite difference, finite volume, and finite element methods. And there have been techniques which have been published as early as the first decade of the 20th century, but it was only around the second half or somewhere around the middle of the 20th century that people came up with a first published results of a computer simulation or computer experiment, and that's when people say that CFD was really born. That's the oldest of the three methods. The basic philosophy of finite difference method is that you try to divide your geometry into something called a structured grid. Now this is what a structured grid looks like. You have a square shape which has been divided into IJK kind of a grid philosophy. So we have I 1, 2, 3, 4, 5, 6, 7, 8 points along the x direction, and say 1, 2, 3, 4, 5 points or 6 points along the y direction, and you have everything divided in the form of a block. Now that's the philosophy of a structured mesh. Even if your geometry is twisted, you can still have an IJK formulation. So this is a structured mesh which is applied for finite difference method. In the lecture on pre-processing software packages, this structured and unstructured kind of meshing philosophy will be covered in detail. But as of now, you can see that the finite difference method is quite applicable on simplified geometries or simple geometries where you can generate such a structured grid, such an IJK kind of a mesh. It is not always possible to actually do it on a real life problem, because you don't encounter such simple geometries like pipe or a duct, a square shaped duct, or a triangular simple shape. We always end up having very complicated geometries. But there are a lot of advantages of finite difference method, which will be discussed still in detail later on. That we have a simple derivation. There are some disadvantages that we can only apply it over simple geometries. And on top of this, the truncation error which I had mentioned earlier, it really seems to suggest a lot of errors, especially for um, when a solution is sought for the flow equations on a very coarse grid where the mesh is not very fine. So if the mesh is too coarse, as it is in some cases. For example, here you can see in the middle the mesh is quite coarse. In such cases, you might have very bad results. So you cannot afford to have a coarse grid everywhere. The finite volume method, on the other hand, it is only around the late 90s that the present form of finite volume method which we are using in most of the commercial packages is used, which is the unstructured grid method. Earlier, this was also a structured grid approach which was applied, and it was let's say around the middle of the 20th century, or later part of the 20th century, that finite volume method started getting more attractive for the people, especially because of the fact that unlike the finite difference method, the finite volume method uses the integral form of the conservation equations, which is derived from the first principles, and therefore it was possible to capture some very interesting phenomena like shock waves. Shock waves could not be captured in finite difference method because it uses the differential form of governing equations. The differential form of governing equations is actually derived from the integral form, assuming that your flow quantity is continuous. Now, as you know, in a shock wave, things are not really continuous. Things have a sudden drop or sudden change in properties across the shock front, and therefore we cannot afford to have this assumption being applied. So in this case, the differential form of governing equation doesn't really hold, which is what is required for finite difference method. So we'll discuss this later on, as we'll see in these slides, in the forthcoming slides. Finite volume method, it can deal with both structured and unstructured mesh, as you can see. And again, the philosophy is quite similar, that we'll try to discretize each and every equation, try to apply it at each mesh point. In this case, these are usually the cell centers or the volumes generated around the nodes. And we try to solve all the equations for a given variable in an iterative fashion, and we try to arrive the solution. The finite element method, this is more of the recent method, so it's only around uh, the late 1970s that FEM method was used for fluid flow analysis. It is in some software packages still used, but it's not very attractive because people are complaining about the conservativeness of the finite element method, which is a very vital property in fluid mechanics and heat transfer analysis. But finite element method was originally used, and it is still very popular for structural mechanics problems, for structural stabilities and dynamics of structures. So it was used for solving the Saint-Venant torsion problem in 1943 by Courant, and it is still being used. And there are some packages still available in the market which are actually based on finite element method, and they are trying to solve multi-physics problems which involve fluid flow and structural analysis problems. In finite element method, the philosophy is quite similar, that we are trying to break down a given geometry into smaller fragments which are called elements in this case, and the methodology is that we try to find out an approximate solution to the governing equations, and we try to minimize the errors. But in all these three cases, what we end up doing is we convert the partial differential equations into linear algebraic equations, which are then solved simultaneously to obtain the solutions. We'll see this example more specifically for the finite difference method now. The finite difference method is actually trying to obtain a numerical solution of partial differential equations. We start with the conservation equation, but as was mentioned earlier, it's in the differential form, so it assumes that your quantities are continuous and differentiable, which may not be the case for shock waves. So therefore shocks cannot be captured using finite difference method, because finite difference method is based on the differential form of the equations. We require the geometry to be discretized. As I mentioned earlier, you require a structured grid, and then we apply something which is the foundation of finite difference method, which is called the Taylor series expansion. So we use the first order term or the second order term as is required, and we try to convert the differential equation into a difference equation, and then we ultimately obtain algebraic equations which are applied over all the grid elements, and we solve them simultaneously to obtain a solution of a given partial differential equation. Let's see it more specifically. So we have the equation or a quantity, let's say x velocity, which has been defined at three grid points, I minus 1, I, and I plus 1. Correspondingly, the x coordinates are xi minus 1, xi, and xi plus 1, and we have these three velocities. What you can see by applying the Taylor series expansion is that you can express ui minus 1 and ui plus 1 in terms of ui and the differentials at ui. So that's the Taylor series expansion, and it contains the higher order terms as well, which I have not written on this slide. If we add them up and if we subtract them, we get the definition of the first derivative at the ith node, and we get the definition of the second derivative at the ith node, along with this term, which when neglected constitutes the truncation error. So let's see the application in a problem. This is a one-dimensional convection diffusion equation you can see here. So this one-dimensional convection diffusion equation, it contains a convection term, it contains a diffusion term, there is no source term, and there is no transient term. It's a steady state problem. And in addition to this, I'm saying it's a one-dimensional steady state problem. So one dimension means there's only derivative with respect to x. It's as good as an ordinary differential equation. But to just demonstrate how finite difference method can be used for such a convection diffusion problem, we're just trying to see how the convection term, as you can see here, the convection term can be expressed as a central differencing equation, which is the difference equation we have obtained by applying central differencing around the node I. And the second derivative, as you can see here, is applied when using the definition which was there in the previous slide. And ultimately we end up, when we put these difference equations in the actual partial differential equation form along with the truncation error, you can see in the previous slide this lack of exact equality is because of the truncation term. But when we try to apply it, we obtain an algebraic equation. So what we have managed to do is, from a partial differential equation which is of this form, this is the conservation form, conservation principle, and we obtain a linear algebraic equation in quantity phi at ith point and I plus 1 and I minus 1. Now when I apply it all over the domain at all the different values of I obtain a set of linear algebraic equations, and when I solve them simultaneously, I obtain a solution to it. That's the basic philosophy of the finite difference method. So what we do is we discretize the one-dimensional convection diffusion equation, we apply using the Taylor series expansion, the difference form. It has advantages. It is simple and effective on structured grids, although there are some disadvantages, especially that it is restricted to simple geometries, especially if you're applying it for a 2D or a 3D analysis. We need to have the possibility to fit in structured grid inside the domain. Just to summarize the overall presentation which we have gone through, we saw how CFD consists of primarily involves the solution of the partial differential equations which govern the flow phenomena. Continuity and momentum define the flow of any fluid, but additionally we can also include energy and other transport equations. And the numerical schemes that we have studied, the finite methods like finite difference, volume, or finite element method, we'll be dealing with finite volume method in the next lecture in more detail. But all these schemes try to convert your flow equations in the partial differential form into linear algebraic equations, and they try to solve for each of the unknowns that you have. In the case of flow equations, these are pressure, U, V, and W. We try to obtain this P at all the different grid points by writing algebraic equations at all these points, and we try to solve them simultaneously. And the unknowns are evaluated at each grid point by solving these equations simultaneously. That's how the numerical scheme works. I hope you enjoyed this session on CFD equations and how we can obtain numerical solutions to them. I hope the assignment sheet which will be provided with this lecture will help you out to answer more specific questions to enhance your understanding of the numerical schemes. And the next lecture on finite volume method will give you more insight into how CFD solvers try to solve the partial differential equations which govern the fluid flow phenomena. Thank you for your attention.